that, you want to construct now another fourth circle, and it's easily constructed. Because this turns out to be the median. Here, in other words, the tangency point of the circle you draw is a median. Now, I want to draw that bigger because you can't see what's happening unless I draw this really huge. So, I'm drawing circles this wide. And so I'm going to label this with where it touches the x-axis. And I'll label this 0 over 1. I'm not going to write this 1 over 0. I'm going to write that as 1 over 1. Because you're going to see the connection here. There's a Stern-Brocot tree hiding in here. Most of the things you read about that don't immediately say that, so. But it is true. Now this one here, that you can fit in here, and this one you can fit in here, it's rather nice because this is 2 over 3. That's where the tangency point is, 2 over 3. And this is going to be 1 over 3. I'm going to do this again. Do it again. It's the median of the two parents. And that's also the way the Stern-Brocot tree works. But it's not, one of the parents lives way up. There's some other stuff I have to tell you before I really go to this. So I'm going to let this sort of sit there. You can stare at it for a while. Well, there are a few more things I want to tell you that I discovered about the Stern-Brocot tree. The way this is going to work is we'll put 0 over 1 over 0, 1 over 1, 2 over 1, 3 over 1, 4 over 1. What's happening here is the next one out here is 2 over 1 and 3 over 1. So this part corresponds to just going out that way. This part in here is something else. So let me show you something. Let's take a number and find it in the Stern-Brocot tree. We have 13 over 44, or 44 over 13. Let me show you about that. So let's write 0 over 1, 1 over 0, 1 over 1, 2 over 1, 3 over 1, 4 over 1, and that was 3. And I think I remember that this was a 2. I think. And this one, that was just a 1, but it still went 17 over 5. And then it goes back this way again. And that was 27 over 8. And then it goes back this way, but only goes back 2. 44 over 13. Now let's ask ourselves a question. Because this was the generalized Euclidean algorithm. How do you find all the xy's? You found the smallest one. That's the one the Euclidean algorithm gives you. In some sense, it's the smallest one. Where are all the other ones? Where do they live on the Stern-Brocot tree? That's a nice question. I've got it written down there. As a matter of fact, I'm going to talk from this paper I gave you. All right. And show you an even more interesting example than this. I didn't number the, oh, I did number the pages. If you have that, this is on page, this is on page 8. So, I'm not going to write the whole tree. I'm just going to start from this part right here. 307 over 69, 396 over 89, 7 over 3 over 158. And over here, I'll come to 525 over 118. Then I'll come back this way. 832 over 187. I could go one more. And what I'll do here is I'll go up to 218 over 39. I'll go up here to 129 over 29. And I'll come up here to 89 over 20. You know what the elements look like. In other words, if I'm looking for this, then all the other ones that's all the other ones, obviously, for any k, positive or negative. But where are they on the tree? We're going to find them on the tree. I'm going to take that as my two numbers here. Okay. Well, for k, I've got them written out there. For k equals 0, that's the one. That's the minimal one. That's the basic one. The one you put in, your generalized Euclidean algorithm gives you. What's a way of describing that? I like to call this the first cross ancestor. Now, if you follow the path of this back up to the base, go in a straight line as far as you can, and the first turn you take, either right or left, is called the first cross ancestor. That's it. That's the smallest one. What about all the other ones? Well, this one right up here is for k equal to 1. This one here is for k equal to minus 1. This is for k equal to minus 2. This is for k equal to, we've already got 1. That's going to be 2. K equal to 3, and so forth. Notice that for all these guys, this is the first cross ancestor. That's just why it works. So, I found something interesting in Ford's paper about Ford circles. I think it was his paper. Very, very interesting. Because you see how these sort of surround this. The way it works with Ford, he asked and answered that same question, but answered it in terms of Ford circles. And what was the answer? The answer was that if you want to know all the other k's, all the x's and y's, you look at all the circles that are tangent to this circle. This, an infinite number going here, an infinite number going there. That corresponds to these two here. The two above it, this one, and I guess for this one, we would look at this and this one. That corresponds to these two up there. So it completely surrounds it. Now you might say, well, how do you get the Stern-Brocot tree out of this thing? Well, it's pretty clear, because I'll just tell you without proving it, because I'm not going to prove anything. It sort of goes against the spirit of this whole seminar. It's important that you're taking the median here. So you say, wow, this guy has something to do with the Stern-Brocot tree. This touches a lot of circles. This is tangent to a lot of circles. And when I'm drawing the Stern-Brocot tree, I've only got 3 things coming into a vertex. You draw a line in the Stern-Brocot tree between 2 fractions here if they are in adjacent levels in touch. For example, you don't draw anything between this and this. Oh, they're tangent though. Here's one down in there. But you have an infinite number, let's say you have an infinite number tangent here. But you don't draw a line from all of those to this. Because this, you don't draw a line from this one to that, even though it's tangent. Why not? They're not in adjacent levels. You only draw a line when they're in adjacent levels. Then you've got the Stern-Brocot tree. Of course, you've got to go out this way rather than going down with the ones that way. Now things began to get interesting. I thought, well, gee, there's such things as Ford spheres. And you can put these Ford spheres over the plane, but you can imagine the plane a complex plane. And you can put the four spheres either over the Gaussian integers or the Eisenstein integers. Let's say you put them over the Gaussian integers. Well, we know that that's a Euclidean domain. We know there's a Euclidean algorithm. There's something wrong, though, with that. With trying to find, for example, if I did something like this, 3 plus 2i plus 1 over 4 minus I plus 1 over I plus 2. Maybe I should write 2 plus I plus 1 over 3 minus 4i. Well, obviously, if I set up the same algorithm that I'd set up for the fractions, it's going to work for these two. In other words, there's an easy way to find out what that's equal to, just by performing exactly the same algorithm. What about the reverse process? Well, once I have a quotient of Gaussian integers that are relatively prime, how do I perform the Euclidean algorithm in such a way that this is unique, that I get those back? Hurwitz had an algorithm, which was sort of, you might call a central Euclidean algorithm, where you're not truncating. Things aren't ordered, so you have to use the norm. That's why it's called a Euclidean domain, because if there is a norm, there is that. So how do you get back to exactly what you have? It's not clear how you do that exactly. There are one algorithm by Schmidt is very complicated, and so I'm working on actually getting a nice algorithm that will get you back to the one you started with. You should be able to, just the same way you do for integers. Now, what's some other questions here? Well, let's say you take the Gaussian integers in the plane. Where are you going to put the Ford circles, Ford spheres? Well, if this is 0, 0, you could put them at exactly the points that are the Gaussian integers. You could put spheres there. It has the same properties of tangency. But now you have 3 parents. And it isn't clear if you have 3 parents whether you can use a three-dimensional version of the median to get the Gaussian rational, because now you're going to be talking about Gaussian rationals. Now, Gaussian rational you can write 2 ways, right? Gaussian rational you can think of 2 ways. You can think of it as either, where there's nothing in common here, or you can think of it as e plus fi, where e and f are both rational fractions. There's an obviously easy way going from here to here. This is slightly more complicated. No, sorry. From here to here is fairly straightforward. You just multiply it by the conjugate and so forth. Going back, so a little more work, not much more work. But the denominator is the sum of squares, and you can factor that. So going back isn't so bad either. But we want to focus on this. So here we have these Ford circles, Ford spheres, and you put these other Ford spheres in the interstices, just like you do for the Ford circles. What do we got hiding in there? Something I haven't found yet. You know what I'm looking for? What am I looking for? I'm looking for a ternary tree having the Gaussian integers, Gaussian rationals, right? I haven't found it yet. I haven't read anything about it. I don't know anybody's thought about it. It's got to be there. If you take the Eisenstein integers, instead of putting 4 spheres, you put 3. You get a tessellation that's the triangular tessellation. There must be a ternary tree containing the Eisenstein rationals as well, and a formation rule, similar to the formation rule I gave for the Stern-Brocot tree, and continued fractions. It's got to be, all this has to be connected, and that's what I'm working on now. Now, this is part of the Apollonian circle idea, where you start off either on the plane or inside a circle, and you just start filling these in everywhere. You're doing it inside a circle. You just start filling in the interstices. There's a theorem of Apollonius, which goes way back, that given any three circles, tangent or not, there are exactly 8 circles tangent to all 3 circles. If those 3 circles are mutually tangent, then there's only an inside circle and an outside circle. Now, if you have hold of a bunch of circles so that 1 over r is an integer, then you've got integral Apollonian circle packings. And that's what Alex Kantorovich is interested in, as well as Sarnak and Lagares and Niels Sloan even, I think. I'm not sure, but the hard thing about that is if they're all integers, what integers occur? That's hard. But I'm not thinking about that. I'm just thinking about the analog of the Stern-Brocot tree, 3-dimensionally, where you have ternary, and maybe you can put general algebraic number fields. It's possible you could do that with higher dimensions. All this stuff about 4 spheres goes into higher dimensions. That's all. That's the end of this talk. Okay, thank you.
Thank you. I will be glad to answer questions.
Okay.